In this video, we'll cover Section 1 of Chapter 12, where we'll talk about one-way ANOVA. We'll learn when to apply ANOVA and how to use that to perform hypothesis tests for a single-factor design, and we'll learn to interpret the results. We'll also talk about a post-ANOVA pairwise comparison test and learn to interpret that. One-way analysis of variance, or one-way ANOVA, really allows us to evaluate the difference between three or more population means on a single factor of differentiation. One thing that makes each of those populations different from each other. This single factor of differentiation, or factor, is something we believe is a cause for the variation between the different samples that we're looking at. We believe it causes variation in this variable that we're attempting to measure. When we talk about that factor is going to have various levels, 3 or more levels. So these are some kind of category or measurement or subgroup that we're interested in studying in the experiment. So we could be interested in studying things that happen in the workplace. One of those things that occur is accidents. We're interested in studying the effect of shift on accident rate. So which shift the worker works is the factor. And the levels of that factor are first, second, and third shifts. There are 3 levels that we're going to compare. The variable of interest might be something like the expected mileage we might get out of a tire. The factor are the different brands of tires that we might be interested in, and each tire is a level. So if we're talking about 5 brands of tires, then we would have 5 levels that we would be comparing. We're going to make assumptions that we've made before. Populations are normally distributed. The populations have approximately equal variances. Each of the samples are drawn randomly and independently of each other, and the data that we're talking about are interval or ratio level data. The hypothesis test that we will conduct for a one-way ANOVA will assume a null hypothesis of each of the means from each of those populations being equal. All population means are equal, or there's no difference between the levels of this factor. There's no treatment effect, there's no variation across the groups. Our alternative hypothesis will be that at least one of those population means is different from the others. So if we're able to reject the null hypothesis, we'll reject the idea that all means are equal, and we'll accept the alternative that one of those levels, or at least one of those levels, is different from the others. This does not mean that all of the population means are different from each other, but at least one, or maybe more than one of those population means are different from the others. So the graph here shows the null hypothesis. We've got these 3 populations, and each of those populations has the same mean. There's no treatment effect, or the factor has no impact on the means of these distributions. If we're able to reject the null hypothesis, it means that at least one of the means is different from the others. So this factor does have an effect. We could have something like this picture on the left, where 2 of the means are statistically the same, and one mean is statistically different from the others. Or we could have the case where all 3 means are statistically different from each other. In order to talk about how we actually test this, we need to learn a new equation. This equation is sum of squares total equals sum of squares between plus sum of squares within. Let's pick this apart. So this piece called SST, or sum of squared total, is the total variation in all of the data. So this looks a little bit like calculating the variance that we learned back in Chapter 3. It's how far each of the individual data values are from an average. The between sample variation, or SSB, sum of squares between, this is also often called the sum of squares explained. This is the variation that we see between the samples that's due to the factor. So this says dispersion among the factor sample means. We're really measuring the difference between the sample means across the levels. Then we have the sum of squares within. This is often called the sum of squared errors or the sum of squared unexplained. This is the variation that occurs inside the samples, and we consider this variation due to sampling. So we look inside a particular level and we talk about the variation inside that level. Let's look at this more closely. So the sum of squares total, or the total sum of squares, that's the SST. What we're doing is taking each individual data point. I represents the population of interest that we've drawn a sample from. The J is the value in that sample that we're looking at. So we look at every possible value from the first sample, and we compare it to this thing that's called the grand mean. This grand mean is actually just the average of all the data points we've collected from all the samples that we're trying to compare. So we calculate this deviation between each of the individual data points in all of our samples to the grand mean, and we square that and add them all up to get this sum of squares total. So this is all the variation that exists in our samples of data. To see this in a picture, pretend that we have 3 samples of data that we're looking at here, and that each of these dots represents the value associated with that data point. The X double bar, or our grand mean, is the average of all 3 of these green dots, all 4 of the pink dots, and all 4 of the blue dots averaged together. The sum of squared total is how far away from the red line, or that grand mean, each of these individual data points is, really that deviation squared. So it's all the variation in the data. The sum of squared between really looks at how far each individual sample mean is from the grand mean and multiplies it by the sample's size so that we can put a weight on how important that deviation is. Again, let's look at this at a picture. The sum of squared between uses the sample mean from the first sample and calculates the deviation from that sample mean to the grand mean and squares it. Then multiplies by the sample size to weight that squared deviation's relative importance. Then we look at the second sample mean and compare it to the grand mean, the third sample mean compared to the grand mean, and so on if there were more than 3 samples. The sum of squares within, or the sum of squared error, this focuses on what's going on inside an individual sample. So you notice we're looking at a particular population I and its sample. Each of the values in that given sample are compared to that sample's mean. We square those deviations. We do this for each of the populations and their relative samples and sum them all up to get the sum of squares within. Back to our picture, what we're really doing is looking at each of these green dots as they compare to that first sample mean. And we're only calculating that variation. And we add to that the variation that we see inside sample 2. So we compare each pink dot to the mean of those pink dots. Add to that the variation that we see in sample 3. This table provides you an explanation of what you'll see in the Excel output that you can generate or in the Minitab output also. Minitab, the order of these columns is slightly different, but the values all mean the same thing. So you see here the source of variation, SS is sum of squares, DF is degrees of freedom, MS is our mean squareds. We haven't talked about those yet, but I'll show you how those are calculated, and F ratio is our F score. So the between samples, it will calculate that SSB for us. We don't actually have to do that by hand. It'll also calculate the SSW for us and the SST. So it's going to calculate the variation that we see between samples, the variation we see within samples, and the sum of squared total. The degrees of freedom for the between part of this is k minus 1. K is our number of populations that we're trying to compare. Our within samples degrees of freedom is n sub t. N is always our sample size. N sub t is our sample size of all of the population's samples added together. Minus k, that k is the same thing that we talked about before. It's the number of populations that we're attempting to compare. The mean square between is the sum of square between divided by the degrees of freedom, or k minus 1. Again, Excel and Minitab will calculate this for us. The mean squares within is the sum of squares within divided by the degrees of freedom associated with the sum of squares within. To do a hypothesis test here, we need a test statistic. This test statistic is going to be called an F test statistic, or an F score. This F score takes the mean squared between and divides by the mean squares within. This will always be a positive value because those sum of squares between and sum of squares within are both deviations squared and then added together. And our degrees of freedom will also always be positive values. So this ratio will always be positive. If this F score, or this ratio, is close to 1, it means that our between variation is not really much different than our within variation. These two numbers are close to each other. So that F ratio, or F score, if it's close to 1, will mean that there's not much variation between factors compared to how much random variation there is in our sample data. We would not be able to reject the null if this value is close to 1. The greater this value happens to be, the more likely it is that we will be able to reject the null hypothesis. hypothesis. So our decision rule here, if the F-score is bigger than an F critical value, which we will draw out of a table or use F inverse in Excel to find, then we can reject the null hypothesis. So if our F-score is big compared to our F critical, we can reject the null hypothesis. Then we know that there's a difference between at least one of the population means that we're considering. So let's consider an example. Suppose you want to see if 3 different clubs yield different distances in golf. You've randomly selected 5 measurements from trials on an automated driving machine. There's a driving machine called Iron Byron that can actually hold a golf club and swing the golf club very, very consistently and drive the golf ball a significant distance. So each club has been placed in the hand of Iron Byron and has struck the ball so that we can see how far Iron Byron would knock the ball with club 1, with club 2, and with club 3. Suppose we want to test whether these clubs perform differently at a 5% level of significance. So we can begin by kind of mapping out the data here. Club 1 is denoted here in these orangish looking dots, club 2 in the tan colored dots, and club 3 in the purple colored dots. We can calculate the average for club 1, that's 249.2, the average for club 2, that's 226, and the average for club 3, that's 205.8. The grand mean for all of those is 227. That's averaging together all of these lengths that the club drove the ball. If we begin to look at this, we might think that club 1 compared to club 2 compared to club 3 all seem very different from each other. But just looking at this at a glance does not give us enough information to reject the null hypothesis and say that these clubs are statistically different. So this slide provides us with an example of how we would do these computations by hand. We're going to allow Excel or Minitab to do this for us. The average distance that club 1 struck the ball was 249. The average distance for club 2 is 226. For club 3 was 205.8. We had 5 items in each sample, so our sample size total was 15, and there are 3 levels that we're looking at here. The sum of squares between compares the sample mean for club 1 to the grand mean, 249.2 minus 227. We square that, we would multiply that by 5, plus the sample mean for club 2 minus the grand mean, square that, plus the sample mean for club 3 minus the grand mean, square that. Each of those pieces would be times 5 because the sample size is 5 for each of them, or since they're all 5, we could add those things up first and then multiply by 5. So the variation between is 4716. The sum of squares within requires us to look at 254 compared to 249.2, the individual strike of the club minus its sample mean squared for each of these 15 sample values. We get the sum of squares within, that's 1119.6. We then calculate the mean squares between, so 4716.4 divided by k minus 1. K is our number of levels, we had 3 levels, and we get 2358.2. Our mean squares within is our 1119 divided by that total number of items in all of our samples added together, which was 15, minus our 3 factors, minus our 3 levels, and that turns out to be 93.3. So our F score, or F statistic, is the mean square between divided by the mean square within, and we get an F score of 25.275. This is the Excel output from the same data. So I went into Data, Data Analysis, ANOVA Single Factor, punched in all that data, and you see those same averages that we were talking about a moment ago. The sum of squares between, the sum of squares within, those are automatically calculated for us, as are the degrees of freedom, the mean squares. Excel provides us the F score and the F critical value. You'll notice this is the same F score that we calculated on the other slide, but it did all the mathematical work for us, and it already went to the table, or F inverse, and found the F critical value for us. You'll also notice that Excel can provide us with a p-value if you like the p-value test better than the critical value test. So to actually conduct the hypothesis test, we have to consider what our null and alternative hypotheses are. We're testing to see if the average for club 1 is the same as club 2 is the same as club 3. And if we can reject the null hypothesis, we're going to be able to say that at least one of those means is different from the others. We assumed a 5% level of significance with 2 degrees of freedom for the between and 12 for the within. We use those degrees of freedom to find our critical value. The F critical value is our cutoff. And you'll notice that the F distribution here looks different than the normal distribution. The F distribution starts at 0 and is lumped closer to the y-axis, and it has a long thin tail that asymptotically approaches this F-axis. That F critical value tells us that to reject the null hypothesis, we need to be beyond 3.885 Our mean squared between divided by our mean squared within was 25.275. So we're out in the rejection region on our F distribution, and we're able to reject the null hypothesis. In other words, we have evidence to conclude that at least one of those golf clubs performs differently than the others. We could also use the p-value test here, and that p-value that we would use to perform this test was actually on this last slide. 4.985 e to the minus 5, which is really 4.985 times 10 to the minus 5, or 0.404985. So that p-value is really, really small. That p-value is less than our alpha of 0.05. Because the p-value is less than alpha, we would reject the null and come to the same conclusion. At least one of those golf clubs is statistically different from the others. If we find that we can reject the null hypothesis, we may want to know which mean or means are statistically different from each other. For example, we might want to know, are mean 1 and mean 2 the same, but mean 3 is different? Or is it something other than this? So this Tukey-Kramer procedure allows us to do these pairwise comparisons to see if we have mean 1 and mean 2 being statistically the same, but each of those means is statistically different from the third. What we'll actually do is calculate the difference between those means in absolute value and compare it to something called the critical range. The critical range is calculated like this. Q sub alpha. Q sub alpha is a value from the standardized range table in the back of the book. We would use K and NT minus K degrees of freedom. Then we're going to multiply that by the square root of the mean squares within divided by 2 times the inverse of the sample sizes for the two things we're trying to compare. So we'll begin by calculating the absolute mean differences for our golf clubs. So club 1 minus club 2. Club 1 was 249.2 minus 226. That difference in absolute value is 23.2 yards. Club 1 minus club 3, we see the difference being 43.4 yards. Club 2 compared to club 3, we see that difference being 20.2 yards. In Appendix J in the textbook, I looked up our Q value with 3 and 12 degrees of freedom for a 5% level of significance and got the value of 3.77. Let's use that 3.77 to calculate our critical range. So I plugged the 3.77 in where the Q was. Our mean squared within was 93.3 divided by 2. For each of our samples, we have 5 items in our sample size. So our critical range actually ends up being the same for all 3 two-way comparisons that we're going to do. When we simplify this, we find this critical range being 16.285. If our absolute mean differences are greater than our critical range, we can say that those two means are different from each other. For each of these mean differences, we see actually that they are greater than our critical range. Because the absolute mean differences are greater than the critical range, we know that there's a significant difference between each pair of means, which actually means for us, each club performs statistically different than the other two clubs. Minitab will actually do these comparisons for us, but you should know where it comes from and what they're trying to compare.